Imagine a $400 metal box bringing a literally billion-dollar pharmaceutical manufacturing line to just a grinding halt.
Yeah, and not because it's broken either.
Right, not because it's broken, not because it's wired incorrectly, and definitely not because it's obsolete. It brings the factory to a halt because the artificial intelligence inside it is, well, from a legal perspective, it's just too smart for the law to understand.
It's an incredibly counterintuitive scenario, to be honest. I mean, we are so conditioned to think that an algorithm's value comes from its boundlessness.
Frank, its ability to learn.
Exactly. Its ability to constantly ingest new data, recognize new patterns, and, organically evolve over time. But when you step into the world of critical infrastructure, that exact evolutionary trait becomes a massive liability.
And that is exactly what we are unpacking in today's deep dive. We are looking at a literal trillion-dollar blind spot in the global supply chain.
It's massive.
Yeah, it really is. And we're using a very specific stack of sources to do it. We have the field notes of Prasad Bhan, who is a deep tech analyst. He basically spends his entire life on factory floors automating medical device inspection.
Right, and we're examining his operational framework, which he calls the quiet architect.
A quiet architect, exactly. And to ground this all in reality for you, we have hard data on platforms actually doing this work. Specifically, we're looking at Switch On Inc.'s Deep Inspect system and how that interfaces with Intel's localized edge computing hardware.
But to truly make sense of all these technical documents, we need a lens to look through. We are going to process all of this through the design philosophy of the legendary industrial designer Dieter Rams.
Yes, less but better. That was his famous ethos, right?
Less but better, yeah. Dieter Rams, he really believed in essential geometry. He believed in unobtrusive design.
Stripping things away.
Exactly, stripping away absolutely every single element that isn't functionally critical. Now, usually when we talk about Rams, we're talking about physical objects.
Like the Braun radios.
Right, the iconic Braun radios from the 1960s, or, the calculators that inspired the first generation of Apple products.
Right.
But in this conversation, we are taking Ram's philosophy of radical reduction and we're applying it to software engineering, to artificial intelligence, and perhaps most importantly, to corporate bureaucracy.
So if you're listening to this, and maybe you're an engineer or a project manager or just someone trying to get an innovative idea past your own company's compliance department, you might think the secret to deploying cutting-edge AI is, writing a more brilliant algorithm.
Which makes sense on paper.
It totally makes sense. But today, we're going to explore why the actual secret to bypassing this massive manufacturing bottleneck is doing the exact opposite.
Yeah.
We're going to look at why you have to intentionally strip away an AI's ability to learn, completely freeze its brain, and just trap it inside a disconnected steel box.
But before we can understand how to build that specific solution, we really have to understand the environment it operates in.
We have to look at the invisible, completely self-inflicted wound that is bleeding capital out of every major manufacturing sector on Earth right now.
It's the ground reality versus the glamour.
Yes. There's a moment in Bond's field notes that is, well, it's both funny and kind of tragic, honestly.
Oh, I know the one you're talking about.
Right. He writes about his family, his relatives, his mother. When they talk about his career, they assume he is building some sort of advanced autonomous AI empire.
They picture a Hollywood scenario.
Exactly. Glowing holographic interfaces, algorithms managing global logistics networks with zero human intervention.
Because the perception of deep tech is incredibly skewed by popular culture. Everyone assumes it's all artificial general intelligence and sentient robots.
But the reality he describes is shockingly administrative. He writes that he spends most of his Tuesdays sitting in windowless conference rooms in Munich.
Not coding a superintelligence.
No. He is literally begging a corporate compliance board to trust a basic 2-megapixel camera bolted inside a metal box. And all this system is trying to do is look for, a scratched printed circuit board, a missing screw, or a misaligned label on a piece of plastic medical tubing. That is the true front line of deep tech.
It is a profound disconnect, and I think it stems from a fundamental misunderstanding of what is actually difficult in industrial engineering.
How so?
Well, creating an AI that can recognize a scratched syringe is relatively easy.
Right.
Getting legal permission for that AI to actually do the job on a regulated factory floor, that is a monumental task.
And the reason those windowless room meetings happen, the reason they are so contentious, is because of the sheer weight of quality assurance, or QA.
Let's talk about the biological realities of that QA burden, because this is really where the capital hemorrhage starts.
Yeah, let's get into that.
When we talk about factories producing microchips, automotive sensors, or, sterile pharmaceuticals, we aren't just talking about a few products rolling down a belt. We are talking about millions of tiny, critical components.
Millions.
And right now, the primary method of inspecting these components relies on frontline QA teams. Human beings standing on a line for an 8-hour shift, manually staring at things.
We are taking human beings who possess the most complex cognitive hardware on the planet and paying them to act like low-level biological sensors.
And biological sensors fail under those conditions.
Of course they do.
The human eye and the visual cortex, they just did not evolve to stare at identical objects moving on a high-speed conveyor belt under fluorescent lighting for 8 hours straight.
What actually happens to the brain in that scenario? Because it's not just a matter of someone getting a little sleepy after lunch, right?
Oh, no, far from it. It's a physiological phenomenon known as visual fatigue, compounded by neural habituation.
Neural habituation. Okay, break that down for us.
So when you look at the exact same shape, say a pristine glass syringe 10,000 times in a row, your brain starts optimizing to save energy.
That makes sense. The brains are lazy.
Exactly. It stops actively processing every single visual input. It begins to anticipate what it should see rather than what is actually there. The visual cortex literally starts editing reality to match its expectations.
Oh, wow. So when the 10,001st syringe comes down the line and it has like a microscopic hairline fracture in the glass,
the operator's eye might physically capture the light, but the brain just paints over it with the image of a perfect syringe.
that's terrifying. The anomaly didn't register at all.
Exactly. And as that fatigue sets in, which is usually within the first hour or two of a shift, defect escape rates begin to climb.
So a cracked syringe makes it into a sterile packaging unit. A misaligned label obscures critical dosage information.
And the financial fallout from that is massive. The plant manager ends up looking at staggering scrap rates.
Right, because if one defective syringe is found in a batch of 10,000 down the line, regulatory protocols often dictate that you can't just toss the one bad syringe.
No, you have to scrap the entire batch.
You scrap the whole thing because you can no longer guarantee the integrity of the lot. You are throwing away perfectly good, highly expensive products.
Or, the nightmare scenario. The defective product escapes the facility entirely and makes it to a hospital.
Which is a whole other level of liability. So the capital leak caused by manual inspection is immense. The plant manager is acutely aware of this. They see the scrap data every morning. They see the exhausted operators.
And their immediate logical conclusion is, we need automated machine vision. We need to install high-speed cameras and artificial intelligence to catch these defects tirelessly, 204/7.
It seems so obvious. You have a vision problem, you apply computer vision.
Yeah.
But this is where the massive collision occurs.
Right.
The plant manager tries to bring in an AI machine vision system to solve the scrap problem. But they aren't the only authority in the building.
Not at all.
Suddenly, the chief compliance officer, or the VP of quality assurance, steps in. They are the control point owners, and they intercept that purchase order and just kill the project entirely.
To understand why that happens, you have to look at their differing incentive structures.
Go.
The plant manager is incentivized by efficiency, throughput, and reducing waste. But the VP of quality assurance, they are incentivized by survival.
Survival.
Their entire mandate is to protect the company from regulatory failure. If an auditor from the FDA or the European Medicines Agency walks onto that floor and finds an unvalidated process, the factory can be shut down. Fines can reach into the hundreds of millions.
So when the software engineers roll in with their state-of-the-art machine learning model, why does the VP of quality panic? The sources frame this as a collision of first principles in mathematics.
It is the ultimate standoff between agile software development and waterfall compliance. Agile software is built on iteration, flexibility, and continuous learning.
Right. Move fast and break things.
Exactly. But regulatory bodies operating under hardware frameworks don't care about flexibility. They demand absolute determinism.
We should define that for the listener because determinism is the bedrock of this entire conversation. What does that mean in this context?
Determinism, in a regulatory context, means that input A must always, without fail, equal output B, every single time.
Okay.
If a mechanical caliper measures a 1-inch pipe, it must report 1 inch today, tomorrow, and 10 years from now. There is no variance, there is no guesswork. The system behaves in a strictly defined, predictable manner.
But neural networks, by their very architectural nature, they do not work like mechanical calipers.
Yeah.
They do not do determinism.
They do not. Machine learning operates on probability arrays. When a deep learning model looks at an image of a medical device, it doesn't output a definitive statement like, this is defective.
Right.
It outputs a statistical probability based on its training weights. It says something like, based on my current internal parameters, I calculate a 99.8% confidence score that this label is misaligned.
Okay, let's unpack that with an analogy, because I think this perfectly highlights the absurdity of the standoff.
Let's hear it.
So imagine you were in a skydiving school, and you are facing a massive backlog of unpacked parachutes. So you hire a brilliant, overly eager intern. You give them a parachute, they pack it, and you ask them, is this packed correctly? Will it open?
Okay.
The intern smiles and says, I am 99.8% sure that it will. Now, if you are an FDA auditor, you cannot audit pretty sure.
No, you can't.
You cannot put a federal stamp of approval on a 99.8% probability when human lives are at stake. You demand a rigid mechanical system that guarantees the parachute is packed exactly the same way 100% of the time.
That analogy cuts right to the heart of it, because to a compliance auditor, that missing 0.2% isn't just a margin of error, it is a terrifying black box of unpredictable risks.
A black box, exactly.
If the AI is only 99.8% confident, what happens in that 0.2% of edge cases? The auditor asks the software engineer, can you guarantee exactly how the algorithm will behave if the lighting changes by 10%?
And the engineer, being scientifically honest, has to say, well, the model will adapt, but I can't mathematically prove the exact output path.
And the moment the engineer admits they can't mathematically prove the exact output path, the audit fails. The deployment of the AI is immediately shut down.
Wow.
The VP of quality rejects the ambiguous model, and the factory defaults right back to human manual labor. They knowingly choose the flawed biological reality of human visual fatigue over the unauditable risk of probabilistic math.
It is a fascinating organizational paradox.
Yeah.
They accept the reality that a human will make mistakes because human error is an established, auditable category of risk. Probabilistic AI error is not.
Exactly.
Which means we are left with this massive self-inflicted wound. Global supply chains are bleeding capital because software engineers are bringing probability to a math fight that strictly requires absolute determinism.
That's a great way to put it.
So if the compliance officers are mathematically and legally justified in rejecting this dynamic AI, which they are based on their constraints, the only way forward isn't to fight the regulators. You are going to convince the FDA to relax their standards on medical devices.
Definitely not.
Instead, we have to fundamentally change the architecture of the AI. We have to bring DRAMs into the software lab.
This is where the concept of operational audacity from Bond's framework becomes crucial.
Operational audacity.
Yeah. If dynamic probability is the enemy of compliance, you must strip the dynamism out of the system. You have to move into essential geometry.
The sources use a very visceral term to describe what must be done to the algorithm here. They say the engineers must castrate the model.
It's an aggressive word, but structurally it is accurate. To bypass the regulatory bottleneck, you have to strip the artificial intelligence of the very mechanism that makes it intelligent.
You have to remove its capacity to learn, adapt, or change. You have to completely freeze the neural network weights.
Let's get technical for a moment so we understand exactly what is being frozen.
Yeah, please. In a standard machine learning model, what is a weight?
In a neural network, a weight is essentially a numerical parameter that determines the strength of the connection between different nodes or neurons. When you train an AI, feeding it thousands of images of good and bad syringes, it constantly adjusts these numerical weights to get better at predicting the right answer. In a modern, cloud-connected AI environment, those weights might continually update.
So it's always shifting.
Right. The system observes new data on the factory floor, tweaks its internal numbers, and theoretically gets smarter over time.
But in a highly regulated environment, that constant tweaking is exactly what the auditor hates. Because if the weights change, the math changes.
Exactly.
And if the math changes, the output is no longer deterministic.
Precisely. So to solve this, the engineers train the model in a closed lab environment until it hits an acceptable accuracy threshold, and then they stop.
They just stop.
They lock the weights entirely. They pour digital concrete over the model's brain. No more tweaking, no more learning, no more organic growth.
What's incredible about this is how it changes the fundamental nature of the software. We're transitioning from dynamic probability to what the sources call static inference.
Static inference, yes.
By freezing those numerical weights and by defining incredibly strict, unalterable input parameters, it stops being an unpredictable AI. It becomes a locked, auditable mathematical filter.
It ceases to be an organism and becomes a calculator.
A calculator.
If you feed the exact same image of a syringe through a frozen neural network 1,000,000 times, you will get the exact same mathematical output 1,000,000 times. Input A now definitively equals output B.
And suddenly, the compliance friction evaporates.
It evaporates because you have finally conformed to the physical compliance boundaries. You are no longer asking the auditor to trust a dynamic probability score. You are handing them a static mathematical equation. You are delivering binary certainty.
But freezing the code is only the digital half of the solution. Where that software physically lives is just as important.
Yes, absolutely.
This is where Rams's principle of unobtrusive design really manifests in the real world. The sources emphasize a critical need to completely remove cloud variability.
This is a major stumbling block for Silicon Valley tech startups trying to break into industrial manufacturing.
Because they love the cloud.
Software developers love the cloud. The cloud offers limitless compute, seamless continuous deployment, remote monitoring, and massive data lakes. But to a compliance auditor in Munich, software floating in an AWS server farm in Virginia is terrifyingly abstract.
Why? What is it about the cloud that scares them so much?
The cloud implies constant, invisible change. It implies latency, bandwidth fluctuations, server updates, and cybersecurity vulnerabilities.
Oh, that makes sense.
If an auditor asks, where exactly is the data being processed? And the answer is, in a distributed server network, the auditor cannot physically verify the boundaries of that system. Hardware, on the other hand, operates in reality. Hardware has a defined perimeter.
So the architectural strategy shifts entirely. You don't send the factory data up to the cloud to be analyzed by the AI. Instead, you push the frozen AI down to the factory floor.
You deploy a localized, completely disconnected edge compute appliance directly on the physical manufacturing line.
We see this extensively detailed in the sources. Intel, for example, catalogs a whole variety of validated, ruggedized edge computing units specifically designed for this.
Right.
They utilize managed runtimes like DeviceWise 6 or platforms like Switch-on Inc.'s Deep Inspect, which runs on Intel's OpenEdge platform. These aren't just generic computers. They are constrained environments that orchestrate the physical data flow locally without ever needing a cloud handshake.
Let's paint a picture of this for the listener, because the aesthetic reality is so far removed from the sci-fi fantasy of AI.
It really is.
When you walk onto the factory floor and look at one of these deployed edge nodes, you aren't looking at a sleek server rack with glowing blue lights. You are looking at a scarred, grease-stained steel workbench next to a noisy conveyor belt.
And sitting squarely on that steel is a heavy anodized matte black edge compute module.
It's industrial grade. It's built to withstand vibration, dust, and temperature fluctuations.
Heavy-duty ribbed black rubber cabling locks into the ports with a hard mechanical click. Next to it is a single, robust industrial machine vision lens focused sharply on a sliver of space where a sterile glass syringe slides into the focal plane.
And in terms of user interface, there are no complex dashboards, no abstract digital nodes.
Just a single red status LED that snaps to a solid green when a good product passes.
It is raw, unvarnished physical reality.
The physical reduction is vital for compliance. It is a tool that does one thing perfectly with absolutely no unnecessary features. But to guarantee that level of perfection, the engineers have to apply another concept from the Quiet Architect Manual: parameter engineering.
You can't just throw the frozen model in the box and call it a day. You have to impose severe boundary conditions on how the box behaves.
Right, you force constraints on the entire system to eliminate any remaining variables. For instance, the sources detail how these systems are often restricted to execute their inference scripts in under 200 milliseconds.
Let's dig into that number. Why 200 milliseconds specifically? Why is that constraint so important?
Well, because in hardware compliance, processing time is a variable, and variance equals risk.
Exact.
If a dynamic AI takes 50 milliseconds to process a clear image, but 300 milliseconds to process a slightly blurry image, that processing time variance could cause the system to miss the next product on a high-speed conveyor belt.
By mathematically forcing the script to execute and fail out if it doesn't, in under 200 milliseconds, you guarantee to the auditor that the machine's thinking time is finite and strictly predictable.
It's about removing every possible dimension of unpredictability. The manual even states they restrict the physical assemblies around the camera to a maximum of 2 moving parts.
2 moving parts. It is the ultimate expression of RAM's less but better. You're engineering away every mechanical variable that could cause a vibration, a shift in focus, or a discrepancy during an audit.
When you look at the entirety of this approach, the sheer brilliance of it becomes clear. You win the game by refusing to play it, by intentionally making the technology rigid, by ripping out its cloud connectivity, freezing its brain, and trapping it in a disconnected steel box. You give the FDA auditor something tangible. You give them a physical object. Yes, a physical object and a static mathematical filter that they can hold, measure, test, and confidently approve.
You've translated cutting-edge software back into the language of industrial hardware.
But having the perfect, unobtrusive physical design is only half the battle. You can build the most beautifully constrained matte black box in the world, but you still have to convince the plant manager to buy it.
And you have to prove to the C-suite that this locked box actually works.
Right. You have to do it fast, without getting bogged down in a 6-month pilot purgatory of endless committee meetings.
Which brings us to the operational execution layer outlined in the sources, the 48-hour protocol.
This is the tactical roadmap. The sources map out an exact step-by-step protocol for getting these isolated edge AI nodes deployed and past regulatory hurdles in just 48 hours.
The entire goal is to generate an actionable validation signal before the bureaucracy has time to strangle the project.
Let's walk through these steps because the psychology behind them is just as important as the technology.
Step 1 is procurement, but it's highly specific. You procure a single industrial-grade edge AI compute node. Not a fleet of them, just one.
Keep the footprint small. Don't ask for $1 million capital expenditure.
Right. Step 2, you install that single node on one high-failure inspection line, but here's the critical part. You run it in purely shadow mode.
The psychology of shadow mode is brilliant. It means the camera is looking at the product, and the edge node is processing the images and making pass or fail decisions. But those decisions are not connected to the factory's ejection mechanism.
Right. It's completely passive.
It is running silently alongside the human operators without replacing them or interfering with the actual production line.
The plant manager doesn't have to worry about the AI accidentally rejecting $1 million worth of good product while it's testing.
Exactly. It drastically lowers the perceived operational risk, allowing the test to actually happen.
Okay, step 3. You execute the locked inference script. This is where you deploy that frozen model we discussed, strictly enforcing that sub-200 millisecond execution time. You prove it can keep up with the physical speed of the belt.
And step 4 is where you generate your auditable proof. You log the deterministic output arrays locally to a CSV file.
Notice the specific format and location. A CSV file. Locally.
You are not pushing complex JSON packets to a proprietary AWS dashboard. You are generating a simple, universally readable spreadsheet right there on the physical hard drive of the edge device.
It records exactly what the system saw, the timestamp, and the binary decision it made, line by line.
Now we arrive at step 5. This is the documentation phase, and when I read this in the sources, I had to stop and reread it.
It's wild.
You take that data, and you draft the initial installation qualification and operational qualification brief, the IQOQ brief. First, for those of us who don't spend our Tuesdays in compliance meetings, what exactly are we qualifying here?
So, in manufacturing, IQ and OQ are standard validation protocols. Installation qualification, or IQ, essentially asks, did you install the equipment exactly as specified by the manufacturer? Is the power supply correct? Are the cables right?
Okay, that's straightforward.
And operational qualification, or OQ, asks, does the equipment operate as intended within its specified operating ranges? Does the camera trigger when the sensor is tripped?
Usually these validation documents are monstrous. I've seen regulatory filings that are 40, 50, 100 pages long.
Oh, easily.
But the mandate from Prasad Bond's framework is that this IQOQ brief should be exactly 150 words long. 150 words. Why so short? How does a 150-word document force a compliance officer to approve a new technology?
The 150-word constraint is arguably the most powerful application of Dieter Rams' philosophy in the entire framework. It's a concept the Quiet Architect Manual calls asynchronous extraction. The explicit goal of this brief is to cancel meetings.
Cancel meetings.
Yes. Think about the psychology of corporate reading. If you hand a VP of quality a 40-page justification report filled with adjectives, flowery language about the future of AI, and complex probability charts, what are you actually doing?
You're giving them a lot to read.
You are inviting debate. You are giving them 40 pages of surface area to question, analyze, and schedule follow-up meetings about. You are creating friction.
Ah, I see. If I write, the highly advanced neural network adapts to changing lighting conditions, an auditor is immediately going to circle the word adapts in red pen and demand a 2-hour meeting to discuss what that means.
Precisely. The 150-word brief removes the adjectives. It removes the surface area. It acts as an API validation structure designed solely for rapid regulatory approval.
The template is incredibly rigid.
Very rigid. It simply identifies the exact physical choke point, explicitly states that the neural network weights are permanently frozen in a locked edge node, and points directly to the attached CSV file to mathematically prove that input A equals output B over a 48-hour period.
And that leads directly into step 6. You present that local CSV data, proving 100% deterministic consistency during the shadow run, along with that hyper-constrained 150-word brief directly to the C-suite.
And because there are no adjectives to debate and no probability scores to question, you force a binary approval decision, yes or no. Does this math work or does it not?
You have boxed the bureaucracy in with absolute, undeniable physical and mathematical truth.
It's structural genius, and once you get that yes on that one specific machine, you unlock a concept called reusable architecture for compliance.
This is how you scale the solution globally without repeating the nightmare every time. The true value of this deterministic validation pack is that it fundamentally minimizes audit time for the entire enterprise moving forward.
How does that work in practice? If a multinational pharmaceutical company has 50 identical packaging lines spread across Germany, Ohio, and Singapore, they don't have to rewrite 50 different validation briefs.
Exactly. Because you aren't auditing the unpredictable intelligence of an AI. You are certifying the rigid architectural framework itself. The regulatory body certifies the physical dimensions of the steel box, the exact frozen weights of the code, and the fixed parameters of the execution script.
You certify that setup once.
And after that single 150-word document is approved, you treat all subsequent deployments as exact physical and digital duplicates. You quite literally copy-paste the setup across the globe.
Because the system is entirely static and hardware locked.
Right. A deployment on a factory floor in Munich is mathematically identical to a deployment on a factory floor in Ohio.
The compliance gap vanishes. The risk is neutralized across the entire corporate footprint.
Okay, I have to pause here because this is where my curiosity hits a wall.
What is it?
If this protocol exists, if it really is as straightforward as freezing the weights, running a 48-hour shadow test, and writing a 150-word brief with no adjectives, why is this still a trillion-dollar problem?
It's a fair question.
Are you telling me that the only thing holding up massive efficiency gains in global supply chains is that software engineers simply refuse to, I don't know, dumb down their brilliant algorithms? Is it just tech ego getting in the way of a mechanical solution?
That is an uncomfortable truth, but a significant part of the delay stems exactly from that cultural collision. You have to consider the training and mindset of modern software engineers.
They want to build the coolest thing possible.
Right. They are taught to build dynamic, learning, elegant systems that handle edge cases fluidly. To a machine learning researcher, taking a complex neural network, lobotomizing its ability to learn, and bolting it to a table feels abhorrent.
It feels like going backwards.
It feels like bad engineering. It hurts their intellectual pride.
They want to build a self-driving car, and compliance is telling them to build a train on fixed tracks.
That is a perfect way to phrase it. But the Quiet Architect Manual aggressively counters this mindset. It argues that true engineering isn't about building the most theoretically sophisticated thing. It's about building the thing that actually solves the choke point in reality.
And refusing to compromise with the compliance department because it offends your tech sensibilities isn't just a theoretical corporate squabble.
No, it's not.
And this is where the story pivots from technology to humanity.
Yeah.
Because that ego-driven friction has a profound human cost on the factory floor. Good design, whether we are talking about a DRAM's Braun radio or a locked-edge AI inference node, must ultimately serve the human user.
This brings us to the core mandate of the entire operating system we're discussing, the philosophy of restorative engineering.
I love this concept, restorative engineering.
The defining principle here is that the ultimate purpose of technology must be to restore human safety, capability, and dignity.
Let's really look at the human toll of the standoff we've been unpacking. Because the VP of quality is terrified of probabilistic AI, and because the software engineers are too proud to freeze their models, who is actually paying the price every single day?
The frontline operators.
The frontline operators. The people wearing the blue sterile gowns, the hairnets, and the high-visibility vests. The men and women standing on the concrete floors. They are the ones bearing the absolute brunt of this failure.
We talked earlier about visual fatigue.
Yes, these operators are physically ruining their eyesight.
Yeah.
They are staring at fast-moving conveyor belts for 40 hours a week, hunting for microscopic cracks in plastic tubing.
They are suffering physical and cognitive degradation simply because the compliance department and the tech department can't agree on a mathematical framework.
It is a profound systemic failure that actively degrades the human worker. When a factory pays a human being, a creature with vast cognitive capabilities, creativity, and intuition, to act as a low-level biological sensor, they are stripping that worker of their dignity.
But when you apply this operational audacity, when you swallow your pride, freeze the AI, box it up, and deploy that locked edge node, you aren't just improving scrap rates.
No, you're doing much more.
You are executing what the sources beautifully describe as an act of unscalable hospitality toward that frontline worker. You are stepping in and automating the brutal visual grind.
And the downstream effect of automating that repetitive inspection loop is remarkable.
Yeah.
You achieve something far more valuable than just regulatory compliance. You restore the operator's cognitive bandwidth.
Right. Because the fear is always that AI takes the job and the operator is left unemployed or just sitting in a break room.
But that's not what happens here.
No. They are freed up to do what human beings are actually evolved to do. Humans are statistically terrible at staring at identical objects for 8 hours looking for a millimeter deviation, but humans are incredible at complex failure analysis.
We are unmatched at root cause problem solving.
Let's play that out. The edgeai node is now doing the boring work. It's watching the syringes, and it suddenly flags 20 defective syringes with cracked glass in the span of an hour.
The AI doesn't know why they are cracked.
Exactly. It just knows they fail the mathematical filter. What does the human operator do now?
The operator, who is no longer visually exhausted, now has the cognitive energy and the time to investigate the systemic failure. They can walk over to the injection molding machine. They can check the temperature gauges. They can investigate the supply chain of the raw glass.
They can figure out why the product is failing in the first place and fix the root cause so it never happens again.
You elevate their role entirely. You upgrade them from a passive biological sensor to an active problem solver. And we are seeing this exact transition happen right now across multiple industries.
We really are.
The data from platforms like SwitchOn Inc. Deep Inspect shows that because their localized systems are validated in Intel's Edge AI catalog, they're being rapidly deployed far beyond just medical devices.
We are seeing this restorative engineering applied in FMCG, fast-moving consumer goods, automotive manufacturing, pharmaceuticals, and complex electronics.
By providing real-time, deterministic data processing directly on the shop floor, they are enabling immediate corrective actions by human operators.
And what I find so crucial to understand here is the empathy required in this kind of engineering. The Quiet Architect Manual insists that engineers must normalize these operational failures.
When an engineer walks onto a floor, acknowledges that manual QA labor is invisible, undocumented, and exhausting, and then builds a rigid, constrained tool specifically to relieve that burden, they disarm the entire organizational ego.
They bypass what organizational psychologists call the crab mentality. When departments are stressed, they tend to pull each other down to protect their own turf. Quality assurance fights production, IT fights engineering.
But when the focus shifts away from, look at my brilliant dynamic AI algorithm, and moves toward, let's fix this exact physical choke point so our operators stop burning out, the culture of the factory fundamentally changes. It's no longer a mechanical fix. It is a cultural fix.
It creates alignment through reduction, which brings us right back to the central theme of this entire discussion. When you observe how we must approach innovation in these highly regulated spaces, what stands out to you the most?
What stands out to me is a massive redefinition of what advanced actually means. True innovation, especially when human safety, legal liability, and strict compliance are involved, is rarely about making the most complex, smartest system possible.
It is almost always about reduction.
Yes, it is about taking a wildly complex technology and reducing it to its absolute simplest physical and regulatory truth. You make the technology so rigid and reliable that it fades into the background entirely. And when the technology fades into the background, humans are finally free to do what humans do best.
Dieter Lams would argue that this is the highest form of design. Less, but better.
So what does this all mean for us? Let's synthesize the journey we just took through these materials. We started by examining a trillion-dollar blind spot in global manufacturing, the massive capital leak caused by manual quality assurance inspection and human visual fatigue.
We observed the fundamental choke point, the mathematical standoff between plant managers who need automated efficiency and compliance officers who are legally required to demand absolute, unauditable determinism.
We learned that the secret to bypassing this bottleneck isn't fighting the regulators, and it isn't writing more complex probability algorithms.
It is adopting the philosophy of functional clarity and reduction. It is having the operational audacity to castrate the AI.
Freezing the neural network weights, stripping away its ability to learn, transitioning from dynamic probability to static inference.
Locking that frozen mind inside a disconnected, unobtrusive edge compute node, like an Intel ruggedized unit.
We walk through the exact tactical execution of the 48-hour shadow mode protocol. We saw how writing a hyper-constrained 150-word validation brief removes the adjectives and forces a binary decision from the C-suite, unlocking a reusable architecture for global compliance.
And ultimately, we saw how embracing these severe constraints results in restorative engineering, automating the visual grind and restoring the cognitive bandwidth and dignity of the frontline worker.
And for you listening, whether you are managing a massive global supply chain or you are just trying to navigate stubborn bureaucratic roadblocks in a completely different field, the core lesson here is incredibly potent.
Think about the last time you tried to get a highly innovative idea past your HR department or your legal team.
You probably walked in with a dynamic, flexible plan, and they immediately shut it down because they couldn't measure the risk.
That dynamic flexibility, which you saw as an asset, they saw as an unauditable liability.
Exactly. Sometimes the only way to get your technology or your project or your idea out the door and into reality is to intentionally constrain it. Sometimes you have to stop trying to be everything to everyone and instead build a very rigid, specific tool for a very specific problem. You have to find the essential geometry of your own bottlenecks.
You have to accept that in the real world of compliance and physical boundaries, adaptability isn't always intelligence. Sometimes adaptability is just risk.
Which brings us back to where we started. We talked about how we expect intelligence and progress to be dynamic and boundless. But we've seen how powerful intentional limitation can be. So I want to leave you with a final provocative thought to mull over long after this deep dive ends.
Go for it.
If we can solve a massive trillion-dollar hardware compliance nightmare and restore the dignity of thousands of workers by intentionally stripping an artificial intelligence of its ability to learn and confining it to a rigid, unthinking physical box, what other unpredictable administrative or corporate bottlenecks in your own life could be instantly solved if you simply stopped trying to be adaptable and chose instead to be entirely inflexibly deterministic?